One of the alternative approaches to the implementation of computations is the approach of adiabatic quantum computing. Before describing this way of implementing a computation, let's remember that the result of any quantum computation is some quantum state that is unlimitedly measured. The purpose of the computation is to get a given state. Let us now assume that some state psi will be the solution to a problem posed to a quantum computer. Let such a state also be ground eigenstate for some Hamiltonian H. Note that such a Hamiltonian can always be found. It can be very complex, but it always exists. To carry out adiabatic computations, we need to perform several stages. First, one needs to prepare the physical system in the ground state of some simple Hamiltonian H0. Next, a simple Hamiltonian H0 must be evolved to the desired complex Hamiltonian H. Such an evolution may be described by the Hamiltonian tilde H of S. Here S is the parameter that we will change in the experiment from 0 to 1. If the perturbation, or in other words, the change in the parameter S, occurs rather slowly, then the system will remain in its ground state. This statement is called the adiabatic theorem. As a result of this adiabatic transformation, we pass from a state corresponding to a simple Hamiltonian to a state that will be a result of quantum computations. It remains for us to understand how slowly the process of adiabatic evolution takes place. In other words, how long do we need to wait in the experiment for the transition to the required quantum state to occur? Since we need the system to be constantly in its ground state, the evolution time can be estimated through the energy gap between ground and the first excited states of the operator tilde H of S. In theory, this time is estimated as big O of 1 divided by delta squared, where delta is the minimum energy gap between the first excited state as a ground state for all S from 0 to 1. Our run of works demonstrated that the model of an adiabatic quantum computer is polynomially equivalent to the circuit model of quantum computer. Polynomial equivalence means that the difference in the time for solving the same problems differ by no more than a polynomial from the input data. D-Wave is currently commercializing this computer model. It is worth noting that the quantum computers of this company are not universal, but are capable of solving only a certain class of problems. This computer is a quantum simulator.